Alright, so in this video I'd just like to go over some of the properties of rings. Pretty much everything I do here is going to be true for any ring in general. Most of them aren't really all that surprising. A lot of them are kind of trivial. They're what you would expect to happen, but I think these proofs are good to see at least once. Properties of rings. Number 1. I'd like to prove that 0 times any element is equal to 0. And that's for all A in R. And again, you'd kind of expect this. This is what you've been told your whole life. 0 times anything is 0. No different with rings. So let's prove this. Proof. And yes, I am going to prove each one of these. They're not really all that hard, but I think they're good to see. So I'm going to start with 0 plus 0 is equal to 0. Certainly that's true. Now I'm going to multiply on the left by a on both sides of this equation. So a times 0 plus 0 is equal to a times 0. Now we have, by the properties of rings, we can use the distributive property here to distribute this a. So a times 0, this 0, plus a times 0, this 0, is equal to, and this side we haven't changed at all, so this stays a times 0. Now, we don't necessarily know what a times 0 is, but we know by the closure property of rings that this actually is an element of R. And also by the properties of rings, we also know that every element has an additive inverse. So I'm going to add the additive inverse for this thing, whatever it is, to the right of both sides of this. So we have a times 0 plus a times 0. I just rewrote this. And now I'm going to add the additive inverse for a times 0, whatever it may be. We don't know. And this is equal to a times 0, that one, plus the additive inverse for a times 0. So I've just added the additive inverse for a times 0 to both sides. Now, this thing, we have an element here, and then we added its additive inverse to it. So this, by the definition of an additive inverse, this is our additive identity, which is 0. So we still have this thing here. Oops. A times 0, and then addition, plus, equals, and again here, we've taken an element and added its additive inverse to it. So this is going to give us the additive identity, which is 0. Now, 0 plus anything, by the definition of additive identity, it doesn't really change anything when you're adding. So this is just a times 0. In other words, this 0 right here just goes away. And this is equal to 0, which is what we wanted. A times 0 is equal to 0. Number 2. I would like to prove that 0 can never equal 1. In other words, the additive identity can never be the same element as the multiplicative identity unless the ring is equal to the trivial ring, just the ring containing 0. And yes, that actually is a ring. So this can only happen if the ring you're working with is just the trivial ring. So to prove this, let's suppose 0 does equal 1. And let's see where that takes us. Scroll down. Suppose 0 does equal 1. Well, I'm going to let's let A be some arbitrary element of the ring. And that's important. This is completely arbitrary. We've picked one at random. So then let's start with A. A is equal to, well, 1 times anything is A, so we could just put a 1 in front of that. This is certainly true by the definition of the unity. But now we can use this fact. 0 is equal to 1, so this is just straight substitution here, 0 times a, and I just proved to you 0 times anything is 0, so that's just 0. Now, by this string of equalities, we have the transitive property, so a is equal to 0. Now, we picked a at random right here. So if we pick any a in the ring, a is equal to 0. So that right there just tells us then that R must be the trivial ring. Because for any a we pick, a is equal to 0. So the only options for a is 0. Number 3. I'd like to prove that a times negative b is equal to negative a times b. In other words, just like you're used to, you can just kind of move this negative around however you please. It really does behave almost just like a negative. You can kind of move it around. As long as there's multiplication here, you can move it around however you like. So I'm going to start with this one by taking the expression a times negative b plus a times b. And I'm just going to kind of work with this and see where we can get with it. So we have an a here and an a here. They're both on the left, so we can use the distributive property of rings. So we can essentially just factor that a out. A times negative b plus b. And if you distribute that in, you'll get this. So these really are the same. Now, we have negative b plus b. So by the definition of additive inverses, this is just the additive identity. So that's just 0. So this is a times 0. And again, we already said a times 0 is just 0. So, again, we have transitive property here. This is one long equation. So a times negative b plus a times b, that's this right here, is equal to 0. Now, we can add the additive inverse for a times b to both sides of this, and that will give us what we want. A times negative b plus a times b plus the additive inverse for a times b is equal to 0, that's this 0, plus the additive inverse for a times b. All I've done is add the additive inverse for a times b to both sides of this. So let's see where that gets us. This thing, I've taken an element, added its additive inverse to it. So this is just 0, the additive identity. We still have this a times negative b here. Negative b plus 0 is equal to, and 0 plus anything is just that anything, so we're just left with this. Negative a times b. And again, this is the additive identity, so adding it doesn't really do anything. We can just get rid of that. So we're left with what we wanted. We wanted a times negative b. A times negative b is equal to negative a times b. Negative a times b. Number 4. I'd like to prove that negative a times negative b is equal to a times b. In other words, a negative times a negative is a positive, just like you expect. So to prove this, let's look at negative a times negative b plus the additive inverse for a times b. And again, let's just work with this and see where it can get us. So using this right here is exactly equal to this, and we just proved that this is equal to this. So we can just substitute that in. So we still have this negative a times this negative b, so that we haven't done anything with that. That stays the same. Times negative b plus, I'm going to make this substitution here, a times negative b. A times negative b. Now we have a negative b here and a negative b here. They're both on the right side. So we can just use the distributive property and factor that out. This is negative a plus a. It's this plus this times the additive inverse for b. I've just factored this b out. Now, this is, again, just 0. We've taken an element and added its additive inverse to it. That gives us the additive identity. And we still have this negative b here. But as we know, 0 times any element is just 0. This is 0. Let me scroll down. So we have negative a times negative b plus negative a times b is equal to 0. Negative a times b, or negative b, plus negative a times b is equal to 0. Now, we can take the additive inverse for this element right here and add it to both sides. So let's do that. Negative a times negative b plus negative a times b plus positive a times b. These are additive inverses of each other, is equal to 0. That's this 0 right here, plus a times b. I guess I'll put that in parentheses since I put this one in parentheses. So we just said that these are additive inverses of each other. So this is just 0. And this one stays the same. We haven't done anything with that. Negative a times negative b plus 0 is equal to 0 plus a times b. So this is just adding 0 doesn't change anything. So we're just going to write a times b. A times b. And again, over here, adding 0 doesn't do anything, so we can just get rid of that. And now we have what we want, what we wanted. Negative a times negative b is equal to a times b. And one more, number 5. Number 5. I'd like to prove that negative 1 times a is equal to negative a. Again, it's what you would expect. Negative 1 times something is just the negative of that. So to prove this, let's start with negative 1 times a plus a. And again, we're just going to start with this and see where it takes us. Well, we have an a on the right on both sides of this. You could think of this as a 1 right here, multiplied by that. So we can just factor this a out. So this is negative 1 plus 1 times a. All I've done is factored this a out. But now we have an element and we're adding its additive inverse to it. So this is just 0 times a. Again, 0 times anything is 0. And now we have a string of equalities. We can say that negative 1 times a plus a is equal to 0. Let's add the additive inverse for a on both sides. Negative 1, wrong color, sorry, times a plus negative a. The additive inverse for a is equal to 0 plus negative a. Okay, so this right here is 0. A plus its additive inverse. We still have this here. Negative 1 times a plus 0 is equal to 0 plus anything is that anything. So we're just left with negative a. And again, 0 plus anything is this, so we can just ignore this 0. So now we have what we wanted. Negative 1 times a is equal to negative a. Alright, so as I said in the beginning of this video, everything I've done here is properties of any ring in general. So if you find a ring, all of this stuff I've just done here holds true. And I think we use these properties all the time, and I think sometimes we might take them for granted. But I mean, we didn't specifically say these were true based off of the definition of a ring, but they can be inferred from that definition, and I just think it's kind of nice to see it.